Hello everyone. Today we're going to explore a fascinating topic in astronomy, supergiant stars. These are the largest, brightest, and most powerful stars in the universe. Did you know that supergiant stars like Betelgeuse or Rigel have masses dozens or even hundreds of times greater than our Sun? But what makes supergiant stars so special? They are the universe's greatest torches, illuminating millions of light years and adding an extraordinary magnificence to the vast cosmos. How are they born, and why are scientists so interested in them? In this video, we'll explore the formation, structure, and vital role of supergiant stars in the boundless universe. First, let's define what a supergiant star is. Supergiant stars are massive stars with at least 10 times the Sun's mass and can reach up to 100 to 200 times its mass. These stars are tens of thousands, even millions of times brighter than the Sun. For example, the star Eta Carinae in the Carina constellation is about 5 million times as bright as the Sun. Supergiant stars play an essential role in the universe. They are factories, producing heavy elements through nuclear fusion reactions occurring in their cores. Elements like carbon, oxygen, and iron are created within supergiant stars, and when they explode in supernova, they spread these elements into space, enriching the material in the universe. These elements have formed planets and even life itself. Supergiant stars are divided into two main types, red supergiants and blue supergiants, each with unique characteristics. Red supergiants are massive stars that have gone through much of their life cycle. Their immense size makes them stand out as radiant red giants in the night sky, showcasing the grandeur of the universe. Betelgeuse, located in the Orion constellation, is a prime example of a red supergiant. Betelgeuse has a diameter around 700 times that of the Sun and is about 640 light-years away from Earth. Blue supergiants, on the other hand, have much higher surface temperatures, typically between 10,000 and 40,000 Kelvin, giving them a powerful blue glow. Rigel, also in the Orion constellation, is a notable example of a blue supergiant. With its intense blue light, Rigel is not only one of the brightest stars visible from Earth, but it also serves as a great beacon in the dark universe, a symbol of strength and power in the vast cosmos. Blue supergiants have shorter lifespans than red supergiants due to their faster fuel consumption. However, both types are essential in the universe, contributing to the life cycle and evolution of other celestial bodies. So how are supergiant stars born? The process begins in massive clouds of gas and dust in space, known as nebula. These nebulae contain large amounts of hydrogen and helium and are considered the cradles of giant stars. Under the influence of gravity, particles in the nebula start to be drawn closer together, forming denser regions. When these regions become dense enough, the temperature and pressure inside increase and nuclear fusion begins. This is when hydrogen nuclei combine to form helium, releasing enormous energy in the form of light and heat. If the nebula is massive enough, the resulting star will have an immense mass and brightness, becoming a supergiant star. These stars will shine brightly in the sky, maintaining a balance between gravitational pull and the outward pressure from nuclear fusion. One of the notable characteristics of supergiant stars is their elemental composition. Most supergiant stars are primarily composed of hydrogen and helium, which make up most of their mass. Initially, about 70 to 75% of a supergiant star's mass is hydrogen, and 25 to 28% is helium. Other heavier elements like carbon, oxygen, neon, and iron make up a tiny fraction, under 2%, but play a crucial role in the star's later stages. As a supergiant star evolves, it gradually consumes the hydrogen in its core through nuclear fusion. When hydrogen depletes, the star's core begins fusing helium into carbon and heavier elements like oxygen and neon. Near the end of its life, the concentration of heavier elements increases in its core, creating a layered structure, with outer layers of hydrogen and inner layers containing helium, carbon, oxygen, and other heavy elements. Additionally, supergiant stars have very short lifespans. Their large mass and rapid fuel consumption mean they last only a few million years, whereas our Sun has a lifespan of up to billions of years. Supergiant stars also generate powerful stellar winds, streams of charged particles blowing from the star's surface at high speeds, like fierce storms sweeping through space. These winds cause the star to lose a significant amount of mass, creating plasma streams in space that strongly affect the surrounding environment and can even stimulate the formation of new stars. This mass loss changes the supergiant star's structure and size, leading to fascinating transformations during its brief but glorious lifetime. Supergiant stars were first recorded and studied in detail in the 19th century, when astronomers began using more powerful telescopes to explore the skies. One of the pioneers in studying these stars was astronomer William Herschel, who spent years observing and recording the characteristics of the largest stars in the universe. In the 1920s, astronomers like Ejnar Hertzsprung and Henry Norris Russell developed the Hertzsprung-Russell diagram, helping classify and locate supergiant stars in stellar evolution. These discoveries opened a new era of understanding the structure and role of supergiant stars in the universe. When Betelgeuse and Rigel were closely observed, scientists were truly amazed by their size and brightness. Initial skepticism existed about how such stars could maintain balance with their enormous size. However, as technology advanced and studies deepened, scientists gradually understood the fusion processes within these stars' cores and the role of gravity in maintaining equilibrium. Supergiant stars play an essential role in the universe's evolution. In their cores, nuclear fusion creates heavy elements like carbon, oxygen, iron, and many other elements essential for life. When a supergiant star reaches the end of its life, these elements are spread into space, enriching the clouds of dust and gas in the universe. This not only enhances the universe's chemical composition, but also provides the foundation for forming new generations of stars and planets. Consider that elements in our bodies, like carbon or oxygen, originated from supergiant stars that exploded in the distant past. When a supergiant star exhausts its core fuel, it undergoes its final stage, an incredibly powerful supernova explosion. This moment unleashes all the energy accumulated over millions of years, creating one of the brightest events in the universe, shining as brightly as an entire galaxy. These massive stars don't fade quietly. They explode like grand fireworks, leaving a lasting mark in space. A supernova explosion is not only the end of a star, but the beginning of new stars and planets. Shock waves from the explosion stimulate the formation of new dust and gas clouds, creating an endless life cycle in the universe. Heavy elements, such as gold and uranium, are also created in the supernova explosion and scattered throughout space, enriching the universe's resources. Thus, supergiant stars are not only colossal, radiant celestial bodies, they are essential in the universe's life cycle, creating elements necessary for life and providing material for new generations of stars and planets. Though they have short lifespans, their impact is immense, leaving a lasting legacy in the universe's history. Thank you for joining us on this journey exploring supergiant stars. Don't forget to like, share, and subscribe to continue uncovering the mysteries of the universe and astronomy.